Now, just like addition did, subtraction has some properties. It doesn't have the same properties, however. For example, subtraction is not associative. That means if we have more than one instance of subtraction in an expression, it matters what order we do them in. For example, let's say we have 5 minus 3 minus 1. Now, order of operations says we do this subtraction first, but I can always write in parentheses anyway, just to highlight what we're doing. So 5 minus 3, that'll give us 2, and then copy down the minus 1. 2 minus 1, that just comes out to 1. On the other hand, right, we could do the second subtraction first if there were parentheses telling us to do so. All right, so here we'll do 3 minus 1 first. That's 1, 2. 5 minus 2, 5 minus 2 is 1, 2, 3. And since on most days 1 and 3 are different, that shows us that subtraction is not associative. Now, for commutative, the situation's even worse. Subtraction is not commutative. It's super duper not commutative. Now, we hinted at that by giving the two numbers in a subtraction expression a different name, right? Remember, these two numbers have different names. This was the minuend, and this was the subtrahend. 5 minus 3, though, we know what this is. We worked it out a moment ago. This is just 2. What about 3 minus 5? If I have 3 cookies, and I eat 5 cookies, it looks like this understanding of subtraction isn't enough to answer this question. There is an answer to this question, but we don't have enough numbers to answer it yet. This is not a whole number. Now, you may know what this is. If so, shh, spoilers. Okay, so subtraction is not associative. It's not commutative. I told you it did have some properties. Like what? If we subtract a number from itself, we get 0. Right, that makes sense. If I have 5 things, and I take 5 of them away, there are none left. If I have 12 things and I take 12 of them away, there are none left. If I have 6,849 things and I take all 6,849 of them away, there are still none left. This one was probably a little bit more time-consuming, right? The same kind of thinking will tell us if we subtract 0, nothing changes. Right? If I have 6 things and I don't take any of them away, I still have 6 things. Right? If I have any number of things and I don't take any of them away, I still have whatever I started with. Now, there's one more property that's going to start to hint at the relationship between addition and subtraction. If I add and then subtract the same number, I get back where I started from. So what does that mean? If I have, say, 3 plus 4 minus 4, I claim I'm going to get the 3 back without even thinking about this. All right, what's happening here? I start with 3, and then I add 4 to it. So I start with 3 things. I get 4 more things. And then I take away 4 of the things. I might as well imagine I'm taking away the 4 new things I just put in, right? So I just have my 3 original things there. Similarly, if I subtract and then add the same number, I get back where I started from. Right, so this is a really similar claim. I claim that if I have, say, if I take 6, then subtract 2, and then add 2, I claim that without even thinking about this, I know I get 6 back. How? Well, so what's happening here? I have 6 things, I take away 2 of them, and then I add 2 back in. Or I could imagine I'm adding these 2 back in. We can also think about these 2 properties on the number line. Right, so here I'm thinking I start with 3. I add on 4, so I'm going to add on a green segment that's 4 long. 1, 2, 3, 4. And then I back up by 4. 1, 2, 3, 4. Oh, of course if I go 4 this way and then back 4 this way, I'll end up where I started from. Same idea here. I start out with 6, then I go back by 2, and from there I go out by 2 again. Alright, so here I've gone left and then right. Here I've gone right, then left. But either way, I end up back where I started from. So this suggests that addition and subtraction have a really strong relationship with each other. They're somehow opposite. We'll see exactly how that works out in the next video.